Hello and welcome. Today we're going to be talking about two-dimensional Fourier series. And it turns out this is related to something that you're probably familiar with before. That is the JPEG file format. Probably one of the most widely used formats for images in the world. And it turns out that it is effectively a Fourier series. So let's talk about Fourier series in two dimensions. Of course, we're going to have x is going to be on some interval 0 to w, that's a width, okay? And then we have y, that's going to be on a range from 0 up to some height, okay? And then what we have are these cosine and sine Fourier series modes. So we have phi n comma m of x comma y is equal to cosine of n pi over wx times cosine m pi over hy. There's another one for the sines. And it's much similar. But in this video, we're going to be focusing mostly on the cosine ones. And it turns out that's because this is the basis for the JPEG. The sine ones, there's nothing conceptually different about them. It's just the cosines are the ones that are going to be used more frequently by us in our applications. So we have over here a few of the things. So we see these are multivariate functions. They have an x and a y in them. And you see that they also do have what I would call just the oscillating modes have independent frequencies in the x and y directions. So we can outline this right here. So in this particular case, we have a picture here of some of these Fourier modes. The upper left corner shows the cosine mode. And we see here we have w is equal to 1 being our width here going across. And then of course we have h is equal to 1 there as well. And here is the cosine 1 mode. So this one cycles through only a half of a cycle as it goes across it's both the x direction and the y direction. So it starts at a high point at 0, 0, and whether you go through the x or the y, you see you're going to basically dipping down through that cosine. So if you start here, you'll be dipping down into the lower levels here. So here we have a heat map where the orange is a high positive number and the blue is a high negative, or sort of a very lower negative number. Likewise, if we go in the y direction, a similar thing happens, right? Of course, if you continue on the cycle through a diagonal, you will eventually increase and find a way to get back up to the peak of that cosine by either increasing x or y. Okay, so that's how the cosine n1 m1 mode works. If I look at the cosine n2 m7, and that's what I really mean here by having independent frequencies in the x and y directions. You see we have an n equals 2 mode, which means it's going to oscillate, go through one cycle of cosine. So in this case here it goes like this, goes down, and then back up as you go through on the x domain. Likewise, if you go on the y domain, if you go on the y direction up, like this, you can see it cycles through not 7 times, but actually 3.5 times as you go through all those cycles of that m equals 7 mode. So clearly there's a higher frequency in the y direction than the x. With the sine modes, of course, very similar things. Here are just some other examples of that. For the sine modes, again, there's nothing conceptually different about the cosine or sine modes. But we're going to focus more on the cosine ones, and that's because it's related to that JPEG. Okay, so the question is, of course, we have to come up with a Fourier series. Well, to do that, of course, we need to define an inner product. So there is actually a 2D inner product. And that's just going to be, if I have a function f of x comma y and a function g of x comma y, then we can define an inner product for these functions to be a double integral from 0 all the way to w, and then from 0 all the way to h, f times g, dA, where dA is going to be dx dy. Actually, I should go back there. It's going to be dy dx, the way I've written it. Okay, so with that, then we can define a Fourier series. So for f's Fourier series, and it's going to be a cosine series, we can write it as follows. It's going to be the sum from n goes to 0 up to infinity. But now we're going to have a double sum, and m goes to 0 and infinity, up to infinity, of a n comma m times our Fourier modes. So here we have an a n m. Our coefficients now, the coefficients have two indexes due to that combination of n and m both being variables. So there's a lot more coefficients to compute to do this. Let's actually define what those coefficients are. Our a n m has a really nice formula. Of course, it's going to be related to our inner product, like that, times a n m, and we have to define this, and this constant right here out front, that's just going to be that normalizing constant. And that normalizing constant is a little bit tricky. They're just numbers, so we can write them down. A n m is going to have, there's three different cases here. One is the standard case, where we're going to have 4 over width times height. Another way you can look at that is actually 2 over w times 2 over h. And we can see that that's a familiar constant that we've seen from cosine and sine Fourier series in one dimension. And that's for when n and m are both positive. Likewise, you get 2 over wh when n is equal to 0 and m is positive, or m is equal to 0 and n is positive. Okay? And then finally, you're going to have 1 over wh for the specific case that n is equal to 0 and m is equal to 0. So those normalizations are a little funky. It's just something you have to worry about when you're going through these double sums. Okay. All right. So let's go on now and further our discussion here. Let's talk about image processing. Okay, we're going to consider that f of x comma y represents, I'm going to back up and say this is actually equal to z, where z is going to be basically a scalar, gray scale value. So what we're talking about here is a black and white photo, and it's going to be a pixel of an image. All right, so in general then, what we're talking about actually is x and y are not continuous variables. They're not continuous variables, but actually we're going to have an xi and a yj are going to be coordinates for all the pixels. Then we'll call it z I and j. All right. So of course this pixel array is what I would call the raw image. And of course, it's an approximation. It's an approximation of some real image that's continuous. So when I say real, I have to put that in quotes because that actually opens up a can of worms that I don't want to really go down. But the idea is that the pixels are going to coarse grain your image a little bit. There's probably more detail that are not picking up unless you have more and more pixels. We'll leave the philosophical discussion of what happens when you focus in and get finer and finer with an image. And rather just say that that such a thing could exist. So of course, when I compute my inner product,
I didn't get that. Try tapping above to edit.
When I compute my inner product, that's going to turn into a numerical integral. So anyway, you're going to have f comma phi n m. Here is going to be some sum over I equals 1 up to n and j equals 1 up to capital M. If you have some n by m image of pixels, so here you have n by m pixels. Okay, and then you're going to have f of xi yj times phi of xi yj, and then you're going to have some delta xi delta yi there. So this is basically an approximate integral, or what we call a Riemann approximation. Okay, so that's how you would do it in practice if you actually have a camera and you have these grayscale images. Again, you're shooting in black and white here, and you want to now come up with these coefficients. And of course, you'd have those a times nm, a times nm on there, and that would get you your your lowercase a and m coefficient that's going to be part of your Fourier series. Okay, so that's another point here, is that one more important point here. If the image is only n by m pixels, it makes no sense to examine high order modes with frequencies much faster, or what I would call fine-grained, than the pixel resolution. Therefore, ANM should be truncated. Okay, so we're going to call that K truncated. So N and M are going to be less than or equal to capital K. They'll start down at 0. So you won't exceed some K value that's going to be your truncation of your Fourier series. So your Fourier series, so the Fourier series will be not infinite. Okay, and this, of course, is a practical issue. And in this case now, the JPEG file format, basically the data of the image, it's really just it's actually just the A, N, M coefficients. And what we can say here is that if you want better image quality, go with a bigger K value. If you want a smaller file, so you want compression, go with a smaller K. Okay, so with that piece of the puzzle put in place, now I want to talk about, let's show an example of one of these Fourier series in 2 dimensions at work, an actual JPEG. So here's an example, and we see an image. The original image here is up in the upper left-hand corner, and it's got a certain number of pixels. It's 320 by 320 pixels. Okay, so you're looking at a very large image, in the 90,000 range in terms of number of actual data points involved. So of course, in this particular case, 320 by 320 is going to be 102,400 pixels. Okay, so the raw file has lots of data. All right, so let's see what we can do with let's see what we can do in terms of compression. Compression via a JPEG. So here I'm going to go with K is equal to 20, and that's up here in the upper right hand corner right here. So if we have K equals 20, so the number of coefficients, the A times N, comma M coefficients, all there's going to be is 400 coefficients. So that's going to be K squared is equal to 400. All right. So we're talking a massive compression. So the actual compression, the file size here, just by storing all those coefficients, is going to be 0.39%. Okay, so much less than 1%. And we can see here the image quality is not good. You see a murky picture that might be a human being. You're not really sure. It's pretty bad. But it didn't cost us very much to create that blurry image. The next thing I'll show you is, of course, if we go to a truncation of 40. Of course, so 40. So if I look at this 40 image, that's going to be 40 squared, so that's going to be 1600 coefficients. Okay, and that gives us a compression of 1.56%. If you see the image here, it's starting to look, it's still pretty bad. I wouldn't say it's a good looking image, but it's clear you can tell what the subject matter, there's clearly a person in this image. You might even be able to make out that the person is holding an ice cream cone, that there are trees, things like that. Very blurry, but it really is starting to come into focus, and still it's 1.56% compression. We're not using nearly as much data as the original image, and we've made huge strides. So now, of course, let's go to the final one here, which is going to be the one here in the lower right hand corner, and that's going to be a K is equal to 100. So of course what we have here is 100,000 coefficients. So in this particular case, I made a mistake here. 100 squared is not 100,000 coefficients. 100 squared is 10,000 coefficients. Okay, so what we have here is a 9.76% compression. And at this point, the image is pretty darn good. Okay, it's still not perfect, yet it's only cost us 10% of the data, roughly speaking, compared to the original image, and we have a pretty good thing. You could probably tell that if I went to a k equals 200 or 300 or something like that, you probably couldn't even tell the difference at that point. And that's, of course, what you do with a JPEG. Your compression is going to be half the size, and you're going to basically be indistinguishable from the original image. So this is truly a compression technique, and it's really important for the World Wide Web, where there's lots of images that you're downloading. Now every image is going to be a fraction of the original raw pixel value. That's what's really important. So in this image, though, I do want to mention one thing. Let's look at that ice cream cone. I'm drawing out the ice cream cone. I'm looking at that cone, and you can see on it there's a waffle cone pattern. Like that. So I'll erase that so you can see it better, but clearly, basically each waffle cone square, each waffle cone square, I would say is about 1/100th of the width of the image. Okay, so it doesn't, and that's just an approximate here, but remember our k is equal to 100, so we're looking at basically the Fourier series can represent variations up to 1/100th of the width of the image. So those variations, I could also call that detail. So it turns out, and I won't show it to you just because I don't want to be too pedantic here, but if you were to go to k equals 90, you wouldn't really be able to see the waffle cone very well. The waffle cone just won't show up. And you can see here, even if you look at the leaves, you can see the leaves there, but you know they're not nearly as sharp as they could be. As you keep cranking up that k value bigger and bigger, you're going to get more and more precise, hard edges. Anytime there's a very, very sharp edge, you'll be able to see that a lot clearer if you have a larger and larger truncation value k. So I hope this just gives you a good picture of like the broad brushstrokes, at least, of like how the JPEG works and the kind of compression you can get. And I think it's really impressive that with just fractions of the amount of data of the original raw file, you can get a really good image coming out of it. And this is why the JPEG is so essential for any kind of internet application. So what we're doing here, what you do here is basically the image. What the image is actually just a set of these coefficients, essentially. All right, so you have all these, and basically that gets sent over the internet. And then when it gets to your computer, so here's your computer here. When it goes in, inside your computer, essentially, your computer it builds the image by taking f of x comma y and doing that big summation. And what happens here, of course, is that these are basically stored ready to go on the computer. These Fourier functions, right? And there's a good way, a very efficient way to summate them. The only thing that's needed is to plug in the coefficients, and it gets that downloaded through the network, and then it generates the image for you very quickly. Because again, these things are already made, hard built into how the computer, how the browser of your web browser would work. It would render images very quickly with some pre-programmed routines to do so. So, and then of course, then you can now view images on the computer screen. Okay, so now I want to talk about one more thing about images. So it turns out we want to look at maybe the energy spectrum. So if we have an energy spectrum, I want to look at that. So recall in 1D, we had the energy spectrum was going to be equal to essentially whatever the coefficient was squared. But now, well, let's say I want to know EK. I want to know about the kth frequency in the image. How do I do that when I have a two-dimensional image? Well, if I look at the ANM, if I put n on this axis and m on that axis, I'll make that a little bit bigger. That'll be A00, that'll be A01, A02, that would be A11 there, and so on. And then of course you'd have a K out there somewhere. And you'd have an A K1, you have an A K2, and so on and so forth. And then you might also have a K up here on the M axis, A0K, A1K, and so on and so forth. So what you have here are those vertical, those horizontal oscillations. And here you're going to have those vertical oscillations. And these are all coefficients with K in it. So what we want to do then is be able to represent the energy spectrum in some compact way. So what we do is we're basically going to sum all of those up. We're going to take 1/2 times the sum of A, K, M, take M of 1 up to forever, plus 1/2 sum over A, N, K, N goes up to 1 and up to forever. Oh, sorry, we're going to start at 0. My bad. There we go. Okay, so this ends up being how you define the energy spectrum, is you have to extract every possible coefficient from the thing. So it turns out, of course, if you sum over K, this will add up to the total magnitude of the function when you plug it into the inner product. Okay, so that's how you define the energy spectrum. Okay, so the energy spectrum actually does really funny things here. So if I study the energy spectrum, if we look at what we call natural images. So this is images that have lots of complexity. All right, and then there's sort of unnatural images. So unnatural images would be stuff that's basically a lot of man-made stuff. Or stuff with lots of repeated patterns. A lot of repeated patterns, etc., etc. So you can see here on the very left side, that would be what I would call a natural image. There's lots of complex stuff. There's both the foreground and background, and you see that there's lots of detail everywhere. There's also lots of, so if I talk about natural images, what you see is that there's lots of detail, but also big regions of light and then dark. You have, so what you do is basically you have complexity at many spatial scales. So you have complexity at many spatial scales, and they actually have a really neat thing that happens here. So they say that basically the spectrum of natural images is power law. So what I mean by that, well, I'll just move this up here a little bit, is that EK of F appears to have a pattern that looks like this. It's proportional to K to the negative gamma. And now what I'll show you up here is that if you take the log of EK, if you plot it on a log scale, what you're going to get here is that. And this becomes here, on a log scale, that is a linear function. So what you can see here, that natural images have this linear function here. They have a specific slope, and it turns out it's very common for the slope to be about somewhere between 1 and 2, usually right in the middle. So in this case, gamma is about 1.5. That's pretty typical. Sometimes it can get up to 2. That's a very typical slope you'll see in a log-log plot. Now let's contrast that with this picture of a brick wall. So clearly there's a lot of repeated patterns in it. So what you find here is you see there's regions where the power spectrum does not conform. This is not really a linear fit. There are aspects of the power or the energy spectrum that don't fit well to a line. And that's because there are frequencies that are overrepresented in the image that aren't well balanced with the rest of the image. And you typically get gamma values that are much, much smaller, closer to 1. So naturally you get 1.5 to 2, and gamma equal to somewhere around 1 for what I would call unnatural. And basically there's a poor fit to a line there. And you see over here in this next picture in the upper right here, there's just another natural image. Here is a landscape with some hikers on the trail. Again, there's both large scale features to the image. There's a horizon. There's a big light patch up where there's the sky, and then there's some dark bits there. And so there's lots of what I would call coarse-grained spatial, large-scale spatial structures. And then there's also places on the image where there's lots and lots of detail. And that kind of thing, again, is going to fit better by a line type thing. And here you get a gamma of about 1.48. Okay, so that's just another example of this phenomenon. And what's neat about it, these power law phenomena, they're also called fractal. And they're called fractal because what they're saying basically is that on any scale, the image spectrum is the same. And we can see that here. If you have log K there, and you have log energy spectrum there, and you have a line there, if I were to shrink the image, just look at this part, it's still just a line. So again, by throwing away and just looking at a subset of the image, you're effectively just looking at the higher frequency components. And what you find there, of course, is that it doesn't matter. It's still the same slope of a line in that log plot, and that is what they call this a scale free property. It's also called a scale invariance. A scale invariance. Okay. So I hope that gives you some perspective on why the spectrum of images is so interesting, and how the JPEG transform, or the JPEG representation, how it's a Fourier series, and how Fourier analysis can teach you something about images by looking at their energy spectrum. Thank you very much.